All right, let's jump right in. Today, we're going to demystify a chemical process that is, no joke, powering almost everything around you, from your body to your car. It's called a redox reaction. And to really get it, we're going to start with a pretty simple question.
I mean, think about it. What could a raging, blazing fire possibly have in common with a quiet, slowly rusting nail? One is super fast, hot, and dramatic. And the other is, well, it's just slow and silent. They seem like total opposites, don't they?
Well, turns out they're both perfect examples of the exact same fundamental chemical process, a redox reaction. And I promise you, once you know what that is, you're going to start seeing it absolutely everywhere.
So, what in the world is redox? Well, the name itself is actually a massive clue.
Redox is basically a mashup of two words, reduction and oxidation. And here's the most important part. Every single redox reaction involves these two things happening at the exact same time. They're a package deal. You can't have one without the other.
To really understand redox, we're going to build up the definition in a few layers. Starting with the very first idea chemists had, it's known as the classical concept, and it's all about one particular element, oxygen. In the early days, the definition was beautifully simple. I mean, it just made sense. If a substance gained oxygen, chemists said it was oxidized. You can almost hear the word oxygen in there. And if it lost oxygen, it was reduced. Easy enough, right? For example, when you burn a strip of magnesium, it reacts with the oxygen right out of the air and becomes this white powder, magnesium oxide. Since the magnesium gained oxygen, we say it has been oxidized. Now, this oxygen-focused view is a great starting point, but it hits a wall pretty quickly. Chemists kept seeing reactions that looked and behaved just like oxidation and reduction, but there was no oxygen anywhere in sight. This meant the definition had to evolve. So now let's get to the modern concept. Scientists realized the real story wasn't about the big oxygen atoms, but about something much, much smaller that was being exchanged, electrons. The modern definition completely reframes things. Oxidation isn't about gaining oxygen anymore. Today, we know that oxidation is the loss of electrons, and reduction, that's the gain of electrons. This is the real core of all redox reactions. Okay, but how are you supposed to remember which is which? Well, with one of the best mnemonics in all of science, oil rig. Just say it with me. Oxidation is loss, reduction is gain. Oil rig. Seriously, once you've got that locked in, you've pretty much got the heart of redox chemistry down. Let's see it in action. Here, a zinc atom gives away 2 of its electrons. Okay, oxidation is loss, so the zinc is oxidized. Those electrons have to go somewhere, and they're gained by a copper ion, which turns into a copper atom. Reduction is gain, so the copper is reduced. See? Oil rig perfectly describes this electron handover. Now, oil rig is fantastic when you can clearly see electrons jumping from one atom to another. But chemistry can be a bit messy. What happens when electrons aren't completely transferred, but are just pulled a little closer to one atom than the other? Well, to handle every possible situation, chemists developed a kind of universal scoring system, oxidation numbers. An oxidation number, or you'll also hear it called an oxidation state, is really just a bookkeeping tool. It's a score we assign to each atom to help us keep track of the electrons, even when they're just being shared in a bond. This gives us our final, most powerful definition. You can forget about oxygen. You can even forget about tracking individual electrons. Just look at the oxidation number. If an atom's oxidation number goes up, it's been oxidized. If its number goes down, it's been reduced. That's it. This works for every single redox reaction there is. Okay, so now that we have the whole picture, from the simple oxygen idea to oil rig, all the way to the universal rule of oxidation numbers, let's see just how diverse this whole process really is out in the real world. And trust me, this process is not one size fits all. Redox reactions are incredibly diverse. Chemists classify them in all sorts of different ways, all depending on how and where the electrons are moving, which gives us this whole variety you see here. For example, on the left, you've got this wild process called disproportionation. In this reaction, the very same element, bromine, is both oxidized and reduced at the same time. Now, on the right is a more standard intermolecular reaction, where one molecule is giving its electrons to a completely different molecule. And this brings us right back to where we started. The slow oxidation of iron into rust and the rapid combustion of a bonfire are both fundamentally redox reactions. They're two completely different-looking processes, but they're both explained by that same simple transfer of electrons. So redox isn't just some abstract concept in a textbook. It's the engine of our world. It's happening in the batteries that power your phone, it's happening in photosynthesis that makes the oxygen we breathe, and it's happening in the metabolism that gives you energy. So now that you know the rules, where else do you spot it?